was another rainy night. I was on my way to meet up with a grad student. It's a new idea to optically measure the coefficient of thermal expansion. Needless to say, I was all ears. Heard you have a way of optically measuring the expansion of materials.
Well, I have an idea using a Fabyr Perot resonator to be exact. Where do you need it?
It's called Time-Domain Thermoreflectance. Let me get a napkin. You're gonna learn something today. You know the importance of nanoscale thermal property measurements, right?
Jesus, those drawing skills. And of course, devices in optoelectronics, quantum computing, and biomedicine are tending towards the nanoscale. That's all you got? Well, now we're talking about feature sizes where material properties deviate from their bulk counterparts. The mean free path of the main energy carriers in semiconductors' dielectrics, or phonons, start to approach material dimensions. When they do, phonons scatter more, slowing energy flow through the material with smaller thicknesses.
Exactly. That's why it's so critical to know thermal properties. They're crucial for future electronics. But the way I find them is optically, with two lasers. Check it out.
Jesus, what is that?
TDTR. It's a pump probe measurement. Basically, it's doing two things. It's pumping heat flux into the system and measuring the sample's response to that input.
Okay, walk me through it.
So you have a beam splitter that separates the pump and the probe beams. The pump beam hits an electro-optic modulator.
So it envelops the laser pulses in a sinusoid?
Exactly. It gives us a reference to compare our signal later on. It then passes through a second harmonic generator. You know what that is, right?
No idea.
I'll give you a hint. It doubles the frequency.
Oh, so it halves the wavelength.
Yup, I even underlined it. Anyway, it goes into an objective that focuses it onto the sample surface.
Okay, so that's all it does?
Simple, right? Now the probe beam. The probe beam gets reflected through a mechanical delay stage.
What does that do?
I'll get into that in a bit, but the beam gets sent to a PBS.
A polarizing beam splitter?
Yup, and this is how it's able to reflect off the sample and go to the photodetector. The photodetector outputs a voltage based on the reflectivity of the sample. The reflectivity is enhanced by depositing a layer of aluminum on top of the sample.
Oh, and reflectivity varies with temperature?
Exactly. We're basically measuring the sample's cooling decay curve. And by varying the optical path length, we can sample points in time along the curve.
Oh, and this is where the delay stage comes in.
Yeah, and the thermal properties are then fit to converge theory and data.
Let me guess, you want to measure the expansion of the sample here, right?
Yes, between the objective and the sample surface. The heat input causes a very small expansion in the sample. And if I can measure the expansion,
you can get the thermal expansion coefficient. Wait, how did you know? I keep my ear to the ground with these sort of things. I've actually been designing some optics already. What? Here, let me get my notebook. I began by seeing where the Fabyr Perot could be placed in your system. Here's a simple Fabyr Perot. You know what it does, right?
It uses two mirrors to re-radiate a field.
Well, its transmission spectrum has huge resonant peaks inside the cavity.
If the distance between them is chosen correctly, it could be used as an interferometer.
But the question is, how do we use it with TDTR? Because you want to measure the change in optical path length along the optical axis, since your beams are coaxial, right? Exactly. I don't want any alignment issues. Well, I think I have a design for you.
If we place a curved mirror between the objective and the sample, we would have two parallel surfaces.
Now you're getting it, where the sample is the second surface.
Then we can measure the expansion of the sample along the optical axis.
That's the plan. Let me show you. My first goal was to see which coating would reflect the probe, but transmit the pump. So I considered a stack like this, with an arbitrary film glass air configuration. Basically, I used the Fresnel multi-layer stack equations. and varied the index of refraction n of the film. I then produced this plot of power reflectance versus n of the film. As you can see, I varied the thickness of the glass. I made it both 1/2 and 1/4 the wavelength of the pump and probe. This tells me I need a coating n of around 2.5.
But can we coat with metals?
Those were my thoughts exactly. It turns out that a layer of glass sandwiched by two metals is best.
Oh, and you varied what kind of metal it was.
Exactly. And each of these metals has a different and complex n at the pump and probe wavelengths. Here are the power reflectance values for all of them. The number at the top of the bars indicates the probe to pump reflectance ratio.
Okay, so the bigger the better?
Yup, and the winner was gold, with a ratio of about 5.
That takes care of one side of the Fabyr Perot, but what about the other side?
Already on it. So here's a stack for the flat mirror. Your transducer layer is aluminum, right?
That's right, with a thickness of 80 nanometers. Okay, good. So I'm assuming an infinite SiO2 substrate for now.
Here are the results for the power reflectance. To recap, this is your overall optical system, right?
Yup, the beams both come in collimated.
Then they go into the objective.
Oh, then it hits the curved mirror.
Exactly, and then your beam hits the sample surface.
So we can just put the mirror in there and call it a day?
Well, not exactly. We need to design a cavity that works.
And that has to do with stability?
Yup, not all cavities just work. Here, let's take a look at a general cavity. In the ray optics picture, we have rays that bounce around in the cavity. If these bouncing rays stay in some domain, or spread,
Then they're stable?
that's right. In the Gaussian picture, they would be self-reproducing. We can write the ABCD matrix for one trip, and come up with difference equations that relate all the rays. We then do a little algebra, and assume a periodic solution, which is realistic, and arrive at our condition where a plus d over 2 must be between -1 and 1. We can express this as the ratio of the length of the cavity divided by the radii of curvature, and make the stability diagram where the blue regions are stable.
So we have to make sure we choose values at places within the blue? Yup, and they'll give us a stable cavity. We then describe our system using ABCD matrices for one round trip. We use Gaussian beam theory to gain all the beam parameters, and sample cavity sizes to optimize constructive interference. Makes sense. Here are the beam radii at both sides plotted with L over R. So how do you choose from all these? Well, we want a size around the same order as the original beam. So I considered lengths that yielded a radii of 10 microns. So here are the final dimensions, highlighted. Nice, so where do we go from here? Well, we look at the power transmission of the cavity, and the resulting sensitivity. As you can see, we're near the most sensitive region given our dimensions and wavelength. I then make use of these equations that give me performance metrics, such as finesse and noise equivalent displacement. Look up some specs on your photodetector. How'd you even get in my... And here are the results. We get a finesse of 43.4, and a noise equivalent displacement of 6.1 femtometers? Pretty sensitive, right? This is great. I need this in my lab. Well, I could build it for you. As a member of your lab.